Isomerism. Isomerism. Isomerism is a phenomenon where two or more compounds with the same molecular formula is a phenomenon where two or more compounds with the same molecular formula exist in different structural forms. Phenomenon where two or more compounds with the same molecular formula exist in different structural forms. There are many ways to define isomerism. Some other persons will say it's a situation whereby two or more compounds having same molecular formula but differs in their structure. So I say it is a phenomenon where two or more compounds in the same molecular formula differs in their structural formula or have different structural forms. So in a nutshell, what differentiates isomers are just their structures. All right. The molecular formula, of course, is always the same. And what is molecular formula? All right, we've not done that yet. Have I treated? I think I've done that. I've treated molecular and empirical formula before now, right? I've done it. Then I'm still going to review it again. Now, what is molecular formula? If they want to ask. Now, this is a formula that shows the actual number of atoms of each element. For example, you can see we have CH3, CH2, and CH3. Okay, let's have something like this. Now, and we also have a compound that presents something like this: CH3, and CH3. Now, if you look at these two compounds, they have something in common. The number of carbons and the number of hydrogens are all the same. That's molecular fuel. First, you ask yourself, how many types of elements are present in this guy? Two types of elements: carbon and what? And hydrogen. Now, how many carbons can we see there? One, two, three, four. Four carbons. How many hydrogen? 10. 3 plus 2, 5 plus 2 plus 3, 10. So you realize that the molecular flow of this guy is equal to each cell, which means the actual number of inside of elements, we have two types of elements that is present here. The actual number of carbon is 4, hydrogen is 10. If you look at the structure of this guy is taking a chain form, like it's taking a chain format. However, this guy, the chain has a branch, right? So the structure of this and this, they are not the same. However, their molecular formula is the same because if you check out this guy, we see have one, two, three, four carbons, right? And then we also have 10 hydrogen. 3 plus 3, 6 plus 3, 9 equals 1, 10. So these two guys are called isomers. And which type of isomer can we call this guy? Chain isomers. It's all right here. Which type of isomers? Chain isomers or skeletal isomers. Why? Because these two guys differs in their chain configuration. One is actually on a straight chain, and the other guy is on a what? Branch chain. So that is basically what the concept of isomerism is all about. So let's look at this guy. Size of isomerism. Size of isomerism. We have two major types of isomerism. The first one is structural isomerism. Second one is stereo isomerism. So we're going to look at this one. Once we're done with this, look at this guy. The next 30 minutes, hopefully, to be done with all there. Structural. It's once you're done with isomerism, then quickly go back. We have three types of structural isomerism. Three types. The first one is chain or the skeletal isomerism. Now I have this one positional isomerism. have the third one, functional group isomers. Now we have chain isomerism, chain or skeletal isomerism, subheading. Chain or skeletal isomerism. Listen down. It's a type of isomerism whereby two or more compounds, the same molecular formula, differs in their chain configuration. Type of isomerism whereby two or more compounds, the same molecular formula, differs in their chain configuration or chain arrangement. Type of isomerism where two or more compounds, the same. Give us an example. We have A3, A2, A3. Now this is N propane. Now propane is actually an alkane that has three carbon chains, right? Now the saying means normal. Anytime you see it means normal, now what does it necessarily mean? When something is normal, it means there is no branch. That's what it means, right? Normal means I have no branch, I'm just normal straight chains. Now, okay, don't let's this guy does not have isomers. So we have this is N butane and CH3 CH. Now this is two methyl propane. Now these two guys, they are chain isomers. Butane, the example I asked you, butane has dash, although they will not ask you because this kind of question is very strict, like it's full pattern the question asks. So they may not really ask you. This one has how many isomers. You know, what they might most likely going to ask you, give the possible isomers of they give you the molecular formula C3H8O. How many isomers are possible for this, and this? Right? The question is more likely going to be tactical. Now, butane has any butane and two methyl butane because once someone says butane simply means that guy has four carbon, right? If you want to draw butane, you can either draw it as this and butane, or you can draw it out. You can actually argue with somebody that this guy can also be called butane, but not in the higher value of the element in terms of the isomers, right? Because the number of carbon, this guy is an isomer of this. This is an isomer of this one here. Alright. So butane has two isomers. Pentane has three. There's a formula we used to use back then, right? But the formula has a lot of deficiencies. It's no longer active from I think 7 or 8 carbon, 8 carbon, yeah. This simply means number of carbon atoms present. For butane is 4. 4 minus 4 is 0. So 2 raised to the power of 0 plus 1. 8 raised to the power of 3 is what? 1 plus 1. So butane has two isomers, this and this. It works for butane, it works for pentane, it works for hexane. I think from octane, it's no longer working. So let's look at pentane. We have when I was in year one, Professor Bushin from chemistry department made me to really understand how you can draw isomers of any compound. And since then, that stick to my head. 1, 2, 3, 4, 5. Now, if I want to get the isomer of this guy, first I'll reduce this chain to 4. Right? So I'll do this is the first guy, NK10. Now I'll reduce the chain to 4 because I want to get isomer that differs in their chain configuration. I'll reduce the chain to 1, 2, 3, 4. Now the last step, I'll use it to move it around this guy. If I put C here, this goes back to this obviously. Obviously. If I put this C here, it's no longer the same thing. It becomes a different compound. You know? So this becomes if I put it here, the same thing as this. If I put it here, I have something new. Right? If I put it here, I still have the same thing here. Right? So this becomes this is a new compound, 2 methyl. I can no longer get another compound from 4 carbon from here. But if I put this here, I'm coming back to what I have here already. You understand what I mean here? If I put this guy, if I want to stop by this start, I'll start off from the side, I'll give this guy the smallest compound. So this becomes 2 methyl with 10. If I put it here, I'll no longer number it from this side. I'll start from this side, which is 1. So putting it here or here is still the same thing. So here becomes this is 2 methyl to 10. I can no longer get another structure from the compound. I'll reduce this guy to 3 carbon. 1, 2, 3. I'll say the real carbon there. So we have 1, 2, and 3. If I take this carbon here and put it here, you know, going back to this. Is it also? If I put it here, I'm still going back to this. Are you aware? So for me to get something new, if I put it here, I have something different. This guy has 5 carbon chain. How many carbon chain do we have here? 2 parent chains have it. How many parent chain here? 3. You can see that the chain is actually shifting back. Why am I taking time to do this? Because they might ask you in exams, give the possible isomers of C3H8O, for example. And some persons will be confused. Even if you did not actually know you don't know this guy before now. But with this explanation of being able to write out the structures and look at the possible placement, right? Can help you to get the answer to this. So here, I'll come here. For me to know the number of hydrogens that will be present on a particular carbon, I'll say 4 minus number of lines. What do I mean by number of lines? Each of these carbon possess line or bond, and our carbon is supposed to have maximum of 4 bonds. Max. So if here is having 1 bond, so for me to know the number of hydrogens that will be present here, I'll say 4 minus 1. That will give me 3. So again, we'll have 3 hydrogens. For me to know the number of hydrogens that will be on this carbon, you can see 2 lines making contact to this guy. 4 minus 2 is 2. This carbon has 3 lines, 1, 2, 3. 4 minus 2 is what? And here we'll have 1 hydrogen. Here we'll have 3. Here we'll have 3. At the end of the day, we are going to check the number of carbon hydrogen. So this becomes CH3. CH3. Now, this is 2 methyl. What I'm doing now, I'm actually increasing our curiosity so that when we actually start talking about making it job, actually make you pay more attention. Now, if you look at 3 of them, they are all 10 isomers because they have molecular total of C5H12. We take this out. 1, 2, 3, 4, 5. 5 happy. 3 plus 2. 5 plus 2. Plus 3. 10. Plus 2. 12. 1, 2, 3, 4, 5. 5 carbon. 3 plus 2, 5. Plus 1. 6. 6 plus 3. 9. 9 plus 3. 12. This is 1, 2, 3, 4, 5. Is it not 3? Hydrogen is 3 in 4 places. 3 times 3 is 12. 3 plus 3, 6 plus 3, 9 plus 3, 12. So that is it. Hexane will have 4. Hexane will have 4, 5 rather. Because this formula can see 1 for hexane. For pentane has 5 carbons. So if I put 5 here, 5 minus 4 is 1, right? 2 ratio of 1 is 2. 2 plus 1 is what? 3. That shows it's 3 isomers. So hexane If I put it with 6 minus 3 is having 2 raised to the box is what? Plus 1. Fine. So let me show us how to get the exam, and also we look at our confidence on how to get isomerism. And after we look at the exam, exam have C6, K14, C6, K14. Can I do it by? All right. So we have to finish experiment today. Do some reaction, reaction. Can I skip the main lecture today? And wait on a break meal. Now the reason why I'm saying so is because the main lecture is actually very very lengthy. So I'm looking for a particular one particular day I'll say this on everything about main lecture. Just read it, you have to read it. All right, let's think it. Some persons that are very slow inside the video. We have some new persons now here. So for say in person is one people. I'll put the we are expecting 5 items. The first guy is 3 pieces. 1, 2, 3, 4, 5, 6. This is the first one, straight thing. And use the check for 5. 1, 2, 3, 4, 5. If I put that egg here, I'm going back to this. You know, so however, if I put it here, I have some DP. Right? Now this is actually not set as this. Now if I put this guy here, I'm actually going to get something with it. I'll say 1, 2, 3, 4, 5. I put this guy. On 5 carbon chain, I can only get 4 of this. I can't get any other one 5 carbon chain. If I put this guy here, I'm coming back to this. So I'm going to use this chain to 4. Right? I'll come here and say 1, 2, 3, 4, 5. I remove this 5. If I put it here, I'm coming back to this zero. If I put it here, am I coming back to you one of this? Right? No. This is a very important. Now, I now say 1, 2, 3, 4. If I put this guy here, I'm coming back to this two also. Yes. But even if I put it there, I'll get a new concept. Yes. I'm following. Now, they may not really asking for all of this. This is just a way of trying to help you. So that in exam, just in case in each compound that is not beyond your scope, you can use this wisdom on the understanding to just get it. Right? Now, so this guy have 1, 2, 3, 4, 5. If you look at them, all of them, if I start putting their carbons, their hydrogens, they will have the same number of carbons and hydrogens, everything there. The difference is that this is straight chain, 6 carbon chain, 5 carbon chain, 10 atom by 2, 5 carbon chain, 10 atom by 3, branch atom by 3, 4 carbon chain, branch points at position 2 and position 3, 4 carbon chain, branch points at position 2. So you come here, you put CH3. Now, so you don't have to ground it, just check it out. You are just explaining how moving isomerism look like. They define in that thing. Now we have this. The total number of carbon here is C4, sorry, C6. How many is that many? 814. So look at it, we have 3 plus 2, 5 plus 2, 7 plus 2, 9 plus 2, 11 plus 3, 14, 6, 3 plus 2, 5 plus 2, 7 plus 3, 10 plus 1, 11. I don't even have to start doing it because I already know that this is correct. So, benzene has 5 isomers. Benzene has, just take note of this, just in case they want to give you guys bonus. Let's continue. Positional, please, we don't positionalize spirit. This is a type of isomerism whereby two or more compounds with the same molecular formula differs in their structure due to the position of the functional group. The type of isomerism whereby two or more compounds with the same molecular formula differs their structure due to the presence of due to the presence. What did I say? Due to the position of their functional due to the position of their functional. Sorry. Type of isomerism whereby two or more compounds with the same molecular formula differs in their structure due to the position of their functional group. Now, have you ever heard of something like butan or butan 1 or butan 2 or in case of letter or? It simply means that maybe you get butan in to in. Every other thing remains the same, just a position number, right? Butan in and butan in means that a 4-carbon chain having a double bond, right? Sorry, there's one more chain. 4-carbon chain with a double bond, right? The first one has a double bond at position number 1. The second one has a double bond at position number 2. So both of them have same molecular formula. The only difference is the position of the functional group. Butan 1 or butan 2 or same thing. So we have the example here. Anytime you hear of a name such that the two names or the three names are the same, the only difference is just the position of a particular functional. You just know it at the back of your mind that this guy is positionalized very. For example, I have CH3, CH2, CH, OH. Please, any compound that has OH as the highest functional group here is called an alcohol. Alcohol is named as alcohol, right? Now, how many carbon atoms do we have in class? 3 carbon alkane is named as what? Now, before we are going to think, but since OH is present here, this will be changed to what? OL. This then becomes what? But this OH, what is the position of this OH on this tab? Position 1, right? So you come here and say what? So, what if I have something like this? I come here and say CH3, CH, CH3. Now this is 2 propan or propan 2 because 3 carbon alkane is still going to be named as what? Propane, right? Once they show it, who they was E and which one? This O is a question number 2. If the number is there 1, it is not 2. We come here and say what? If you notice, the names are the same. The only difference is what? The position of the what? So this type of iceberg, we call it what? We say the type whereby we both have same molecular formula. If you check this guy, this is C3, 1, 2, 3. The H is 3 plus 6, 5, plus 2, 7, plus 1, what? 8. This was what I gave us earlier. Remember, I wrote something like this because they have asked this question a couple of times. They'll say, give the possible isomers of C3H8O. Now, the question being anything you can think of that will have this molecular function and then have a correct structure, give it to. That's what it means. So you can see this. This is actually positional isomerism or positional isomerism. Isomerism is a phenomenon. Isomers are the compounds in form. So this and this are isomers, not just isomers, positional isomers. Why? Because the functional group, which is in this case in the OH, is what is different in their position. The chain is saying carbon, three carbon chain is also. The OH is at number 2 and the OH is at number what? 1. It is number 1. You start counting from the carbon that have the OH. Here is like H. So let's look at the next example. So please do this. Two of these are molecular formulas. C3H8O. Please. Another example of this guy, please. It must not be body. Like I have CH3, CH2, CHGR, and CH3, CH3. This is one global propane. And this is what? What is the difference between both of them? Question on what? So look at this guy is 1, 2, 3, 3 carbon chain. This guy is also 1, 2, 3, 3 carbon chain. In this guy, the propane is at number what? In this guy, propane is at number 1. So you notice that apart from the position of the pH, the two compounds would have been the same. In fact, they are the same apart from this guy. So the name of this guy is Bromo does not have the power to change the energy key of as alkane. I told us here. This on 9 this is one bromo propane. Why? Propane is very straight, 3 carbon alkanes. Bromo is VR and approach number 1. You number from the side that will give you a because in this number. Right? 1, 2, 3. 1, 2, 3. So this guy is at number 1, this guy is at number 1. So this is 2 bromo propane. They are molecular from like C3 and this is H7 VR. We also have the example is the sponge. So we also let me just give us the ones that are very, very common in the example. We have each one in case they can just do copy and paste. Because this is one in. Why do we call it this one in? This is 4 carbon alkane, 4 carbon chain, right? There's a double bond and position number 1. If you start numbering from here, this is the first carbon bearing the double bond, it's not so. If you start numbering from here, this double bond is at number 2, it's not so. So the position of the double bond here is that position number 1, right here that position number 1. So that is the only difference between these two guys. They are actually having kind of straight chain, not so. The difference is that this guy has double bond at number 1, this guy has double bond at number 1. So that's all this thing. So this is good. 1 in. Okay, this is, let's say, this is 2 between. And this is 1 between. Once a double bond is present in a compound, 4 carbon alkanes is supposed to work. 4 carbon alkanes is supposed to be the same. Alright, so I said this since I list out this guy, please the next what we're going to be looking at the functional group isomerism. Now, functional group isomerism is a type of isomerism whereby two or more compounds with the same molecular formula differs in their structure due to the position of different functional groups. Right? Now, before we proceed, it is important we actually understand what functional group is So functional group I say is an atom. It can be an atom, or it can be a group of atoms, or it can even be a bond, right? So it can be an atom, it can be group of atoms, it can be a bond. Okay, so functional group is an atom or group of atoms that determines the chemical reactivity of a compound. That determines the chemical reactivity of a compound. Now, we have some common functional group. We have the first one, alcohol functional group. Because this is what the hydrogen is actually where it's being attached to the compound. We have the ether functional group. Ether has oxygen with two hydrogen, meaning that when this oxygen is attached to carbon, when the oxygen is attached to two carbon, the example we have CH3 or CH3. This is actually an ether. Please bear this at the back of your mind. Ether is actually oxygen bonded on both sides by carbon. So this is a functional group of ether. The general formula for ether, when we start talking about ether, this is the general formula where the two R's and the alkyl groups. Right? So anytime you see an O in the middle being flanked by both sides, that is actually an ether. So another example we have alkene. This is just a double bond. We have diene. But diene means what? Diene means what? In means what? Double bond. Anytime you see in, it's a double bond. Huh? Diene means double bond. So this is how it going to look like. Now look, we have alkane and we have another one. Alkynes. We have so many of them. I'm just putting these together so that when I start taking examples, it's not going to look strange. We have COOH, and this is carboxylic acid or alkaline acid. Also, we have esters. So let's look at these six examples. Using can solve problems and then we'll move to the next type of isomerism. So for any compound to exhibit functional group isomerism, two different compounds with the same molecular formula, but will possess either of these. One of them can possess OH, and the other will possess ether. And you realize that they will have the same molecular flavor. In another case, one of them can possess diene, and the other will possess alkyne. Class, take this up. Now let's come back to this. What is functional group isomerism? I'll give the example. Let me just give us a little example before I give this up. Imagine I give you something like this. And platform. The two compounds have same molecular formula. Carbon is 3, sorry, carbon is T. Hydrogen is 6, oxygen is how many? 1. Now look at that guy very well. But you notice that the arrangement is actually not the same. And what is making the arrangement not to be the same is because of the type of functional that is spreading. Here, which type of functional is spreading first? Better. When O is flanked on both sides by carbon. Yeah, this type of functional is spreading. So you notice that irrespective of the fact that both of them have same molecular formula, right? But their structure is not the same. And what is causing the difference in their structure? Functional group. So these two guys are classified under functional group what? So this is an example. So this guy is dimethyl ether. I will explain why we call it dimethyl ether. Just write it down. And this guy is ethanol. I will explain why it is called dimethyl ether. So you can see that in exams, two ways, or there are different ways this question. I don't want to call for past question. Once I'm done with isomerism, I'll call for past question. So just look at how the question was said. Please, I don't want to create this so that you're going to be telling me the type of functional that I'm present. This one is ether. This one is alcohol. But in regard to it, I have 10 molecular formula, right? Now, the next example I'm about to give us now. Okay, let me name this guy. Why do we call this time ethyl ether? Alright, ether. Hello, please. Ether is different from ether, right? The ether in organic chemistry is not the same thing as ether. Anytime you see a compound that have both flanked on both sides by carbon, anytime you see a compound that has O in the center, flanked on both sides by carbon, the name given to such compound is ether. Simply means anytime you have oxygen flanked on both sides by carbon, right? It's ether. Now, how do we name ether? Why do we actually say that it's ether? There are two ways to name ether. You can either name it as ether or name it as alkoxy alkane. I'm coming to that. Now, the rule says, like what I'm doing now, like I said, this is for me is one of the best way to teach because if I'm doing this short explanation, when I now start the main rule, just like somebody giving you something to taste, right? And then later they give you the name, it's not. So now look at this. If I have something like this, the rule says, name the alkyl groups at the left hand side, name the alkyl group at the right hand side. Also, if they are different, arrange them alphabetically. And at the end of the day, put the word ether. This look at me. If you look at this guy, there is O here. On the left hand side, we have C, carbon, right? Yeah. Right hand side, we also have what? Carbon. So this is ether because this O is flanked on both sides by carbon. So let's name this guy. What is the name of this alkyl group? HCl. What is the name of this alkyl group? Are they the same? No. He and most of them confess alphabetically. So this guy will be HCl, methyl what? Ether. Right? Now this guy, what is this guy? What is this guy? So if you say methyl, does it make sense? Anytime things actually appear, take one and it will multiply, right? Yeah. So two of methyl are root one, and I put one. Right. This guy now becomes that methyl what? Yeah. Because they are the same. If they are not the same, you do it alphabetically. Then the methyl, then the methyl, and add the words. Do you understand now? Yes. Let's go. Which type of functionality present in this first compound? Dying, right? Yeah. Which type of present here? So sometimes they can just ask you the exam. The functional which type of isomerism is executed by dyene and alkyne? What's the answer? Which type of isomerism is executed by a dyene and an alkyne? What's that isomerism? Which type of isomerism is executed by ether and alcohol? Still functional. So that's one of the three. Now this guy is a dyene. But that one can be like this one is inconsistent. That's inconsistent. One minute now. This is a dyene. This is an alkyne. The constant here is not the same as this, but the molecular formula is the same. Now, you go to name a dyene. Look up. Let me just give you the nomenclature briefly. dienes are named as what? The ane that ends an alkane. These two guys, it's always to remove it, right? But one carbon alkane is methane also. Four carbon alkane is what? Four carbon alkane is what? How many carbon do you have here? Four. One, two, three, four. It's also. Methane is also. So if I come here, I'll say methane. But since you can see two double bond here, you remove the words. Any. Because if you don't name two double bond, it's named as alkyne. The alkane, this guy is removed and replaced with what? Nine. So for butane, I'll remove this guy, right? Now I'll remove this. Now let's number this guy so that we can get to the position of the double bond. Like say 1, 2, 3, 4. The number is from the side that will give the double bond the least or the smallest number. The first double bond is attached to the first carbon here. This is position 1. It's not 2. Yeah. 2. The next one is attached to position what? 3. So you come here and say, either you say buta die and come here and say 1, 3. So that anybody that sees this knows that on a 4 carbon chain, right? We have die. That's having of what? That's the 4, right? Yes. And position what? And what? Or you can name this guy as one. Sorry. This is 1, 3, not 1, 4. How many carbon atoms can we see here? 4, right? Yes. Now, 4 carbon alkane is supposed to be what? The same. Now, remove the Y. Who think I put what? Right, that is inside, right? But if it's not correct yet, right? We must tell which position that Y, that triple bond is attached to. We always ensure you do that. The first carbon out of the number from the side that will be this guy is one x of also. If you come from this side, this is 1, 2, 3. The first carbon during the triple bond is at number 3, right? Yeah. If you start from this guy, this is 1. So 1 and 3, which of them is the smallest number? 1. So this guy becomes 1 time or 1. Please, you know that the 6 like what? Time. You see the same thing. I just have to like who does that is not the same. I just want to see how you do one. Anytime you have 1, you can always ignore the 1. Because 1x, you don't need to add a 1 in front of it. You just write it as 1. Yes. But if the position number is not 1, if it is 2 and above, you must do what you must add it. Alright, so this guy is with 1 eye. Let's take something. Let me show something now. They can also give us with 2 eye. What if they give us with 2 eye? Are we seeing it to have the same molecular figure? So it means that in exams, they can say with a 1 3 eye and with 2 eye adapt. We must always do with 1 eye. And it look at it. What if I turn here and I will say 1, 2, 3, 4? I pull out the triple bond for position 1 and I put that position 1. 2. I will not have hydrogen here. Why? Because I told us that carbon is supposed to have maximum of having bonds. For it to know the number of hydrogen on a particular carbon, subtract the number of bonds from what? From 4. Now, how many carbon or how many lines can you see making contact with this guy? 1, 2, 3, 4. So you say 4 minus 4, you get to your 4. This guy will have many hydrogen. Number of hits on a particular carbon is always 4 minus number of lines or bonds on the carbon. So if I want to know the number of hydrogen I'll be here, I'll simply say how many lines or how many bonds is making contact with this guy. One, two, three, four. 4 - 3 is 0. So this guy will not have any hydrogen. This guy is having just one line here. 4 - 1 is what? 3. So you get the what? 6 and you have the what? Now if you look at this is good two what? The I is an upper two. Unlike this one that the I is an upper one. So if you notice, buta one straight die and but one I are positional isomers. Or buta one three die and but two I is still what? Positional isomer. Why? Because they have same number of carbon and hydrogen for different functional groups. Eh? Say what? What did I do? That's coming back. Stereo isomeric. Stereo isomeric. Listen up. This is a study of the arrangement of atoms in space. It's a study of the arrangement of atoms in space relative to one another. It is a study of the arrangement of atoms in space relative to one another. Now let me explain some. Please pay attention. Although at this level, at this stage, you don't really need it. But for those of us in pharmacy, DIC, or chemistry, MCB, if there is any here, you'll get going to need it when you get to 200 level. Now, isomers and stereoisomers are isomers. But there's something spectacular about stereoisomers. Stereoisomers, they have same molecular formula. They have same structure. They have same what? But what actually differentiates both of them is the arrangement of the atoms in space. Example, have you heard of cis and trans before? In cis and trans, they always the cis and the trans will always have the same structure. You always have this structure back. The only difference is that in cis, maybe what is up will no longer be what is up. So now it's just but in terms of their structure, is the same. Both the cis and the trans will have this structure. The only difference is just the arrangement of the atoms in space. If I have this here, two same type of software on the same side. CH3 is up, H and H is what? Down. I come back there, I have CH3 here, I have H3 here. And you notice here, CH3 and CH3 is no longer up. They are now what? Opposites. One is up and one is what? Here, both of them will what? So what is the difference between both of these? Their structure is the same. Their molecular formula is also what? What differentiation then is on their arrangement in phase. This one is up and this one is what? So somebody asks what makes stereoisomer different from this guy? In the case of normal isomer, same molecular formula, different structure, right? Stereoisomer, same molecular formula, same structure, different arrangement in what? Phase. Sometimes people use physical arrangement, spatial, or they call it space arrangement. Okay, types of stereo isolation. We have geometry, isomerism, and optical isomerism. We have geometry, we have optical. I'm trying to find. All right. It's on YouTube. Let's start the first one. So maybe let's not basic iceberg. This now. Geometric isomerism compose as a result of restricted rotation. Geometric isomerism compose as a result of restricted rotation or lack of rotation. Stop. Or lack of rotation. Stop. This is found in carbon-carbon double bond in alkene or carbon-carbon single bond in a ring compound. So like I said, that maybe in case you ask, what causes the geometric isomerism? Okay, for something to exist, geometric isomerism, the first condition has to be that that guy does not or that guy experiences restricted rotation as a result of either double bond or so. Please put out conditions for compound to explain geometric isomerism. Condition for compound to explain geometric isomerism. Number one, presence of a double presence of a double bond or a ring compound. Presence of a double bond or a ring compound. Now the next point I would like to draw here is that now not all alkenes, because all alkenes possess double bond, but not all compounds with double bond exhibit geometric isomerism. So that is where condition number two comes in. Listen and listen very carefully. Before you write down this, let me explain. This is two carbon bond. If here is CH3 and here is CH3, this compound, irrespective of whatever is on this side, will not exhibit geometric isomerism because each of the carbons of the double bond must not have two same directions. Must not have what? This guy is and this guy is it's not they are the same. So this has failed condition number two. So if I have something like this, here is H and here is H2. Here is H and here is H2. This column has no geometric isomerism or will exhibit geometric isomerism. Why? Because each of the carbons of the double bond, each of them, you consider it each, right? Individually, they are having different substances. H is not the same as CH3 on this carbon. On this other carbon, H is not the same as CH3. If I come there and put H3N, can you say it's geometric isomerism? Yes. Yes, because each of the carbons of the double bond, they are not having the same type of substance, right? So that is also condition number two. It says each carbon of the double bond must not have two same type. So it's best we actually know compounds that can exhibit geometric isomerism. Once we are done with that, we switch into how to name them. This and that, here and there. And then we look at opticals and their zone. So now what I do, These two conditions must be met. First, you have to see a double bond or you have to see a ring. Second, the two carbons that are involved, either the two carbons in a ring or the two carbons in a double bond, each of them must not have the same type of substrate. Because if they have the same type of substrate, they cannot really study the arrangement in space. Considering this guy, H and CH3 is not the same, so this carbon are passed the test. Considering the second guy, the H and CH3 is not the same, so this carbon are passed the test. So once both of them are passed the test, you can explain geometrical isomerism. But what if they take whereby the first carbon passed the test, whereas the second carbon failed the test? Would this compound explain geometrical isomerism? No. So please tell me this. Which of the following, alright, just tell me, which of the following would explain geometrical isomerism? CH3. The first or the second? Look at that. You know, between this and this, something would explain geometrical isomerism. The first one is the correct answer. Now, this second one is wrong because first thing first, is there a double bond in that compound? Yes, but in the ground, just one accelerate the two carbon of the double bond. Accelerate that place there. You come here, put an asterisk, put a what? No matter how big the compound is, just locate the two carbons of the double bond. That is it. Now, let's look at the carbon. This guy is having two same type of substance, CH3 and what? CH3. What is going on back? Must not have same type, right? Yeah. Is this guy having same type? Yeah. So those are chose this guy, and you know why. This guy is correct. Because this carbon needs CH3. This guy has this H can be like this. It means that the two carbons of the double bonds are the ones with the asterisk. If you asterisk this guy, we have H, we have CH3, we have H, and we have CH2. So, Alex, you understand now? There's some times you can even give a compound that contains a triple bond and say this triple bond cannot exhibit the medical number. Can it exhibit? It cannot. You know why? Why? You know why? Because for any carbon, for anything to exhibit the metric isomer, you must have two substrates on the carbon. But the triple bond can only have one substrate. Because if I have one, two, three, carbon can have just four bonds, right? One of them are taking three already, leaving us with just what? One. So this cannot. Because you cannot have the metric isomers can be named using the six strands system of naming. Geometric isomers can be named using the six strands system of naming. For C, I'm going to explain this. Before now, a geometric isomer is named as six. A geometric isomer is named as six when two same type of substrates on both carbons of the double bond. Geometric isomers are named as six when two same type of substrates on both carbons of the double bond are on the same side. When two same type of substrates on both carbon of the double bond are on the same side. when two same type of substituent on both carbons of the double bond are on the same side. That's it. For trans, the metric isomers are named as trans when two same type of substituents, on both carbons of the double bond are on the opposite side. When two same type of substituents on both carbons of the double bond are on the opposite side. So we have something like this. We have so we have the first one, C. Now it's a normal structure of C. C is the Now I want to put this in the geometric form. I'll come here, the two carbon on the double bond, I'll put asterisks. So you come here to have the two carbon on the double bond at the center. Put this guy, push it this way. This is more like there's H here, and then another H here. This is H, CH3. This is H, CH3. Now, once you see the center of this, so this guy is 2A. But since it is written in this form, it's not a geometric form. And in geometric form, you either read 6 or trans or E and Z. But at this level, you are taking to 6 and trans. Now, first, the name of this guy is with 2A because it is this compound that we transfer the still also. So this is equal to 2A. But you cannot say it this way because the moment you put it in this form, this is not a geometric form. You have to tell whether it is space or what. Now, we said for sales, two same type of substrates on both carbons of the double bond are on what? Now, the two carbons of the double bond. H on this guy is up. H on this other guy is what? Same side lost. CH3 is down. CH is what? Yeah. So, is it cis or trans? Cis. So, you come here, it becomes the. Can you tell us to for this one? So, this is cis with 2A or cis 2C. Now, the second guy would be CH3 again. CH3 again. H. Now, looking at the definition I gave us for trans, I say a trans is a case where two same type of substituent on both carbons of the double bonds are on what? Opposite side. So this guy, this is up and this is down. So that's opposite. So this is what? Trans. So therefore, note C and trans are which type of isomers? So in exams, they could just say C is good 2A and trans between are that type of isomers. What's the answer? Not also, there's also what we call E and Z, just in case. E and Z isomers, E and Z compounds are also. Now, this one should not be here of your head. In case an exam, they just want to say something that they expect you to know from the textbook because I know E and Z sometimes inside the text. So just know that cis and trans is a geometric isomer. E and Z is a geometric isomer. As a matter of fact, C is same thing as Z. Trans is same as what? That's right. So another name for there are compounds that you can use C and Z. I don't want to go into detail. It's optical. All right. Now, when they say optical isomeric, from the word optics, physics 115, optics means light. One of my best. So please, let's write. Since you've understood the concept, optical isomerism is exhibited by compounds that are optically. This is recorded. Yeah. Optical isomerism is exhibited by compounds that are optically active. That is, compound that can rotate plane polarized light. Optical isomerism is exhibited by compounds that are optically active. That is, can rotate plane polarized light. Alright. For a compound to rotate plane polarized light, they must possess at least one chiral carbon. For a compound to rotate plane polarized light, they must possess at least one chiral carbon. It is in brackets as mentioned. Uh, they must possess at least one chiral carbon. In brackets as metric carbon. Now, what is a chiral carbon? Question mark. What is a chiral carbon? Because we introduced chiral carbon, so we need to understand what a chiral carbon is. Let's put down a chiral carbon is a carbon atom that has four different substituents attached to it. The carbon atom that has four different substituents attached to it. Carbon atom that has four different substituents attached to it. Okay. Now, an example of such we have something like let's say CH3, CH2, CH, CH3, OH. Now, this here that has asterisks is a chiral carbon. We want to ask why? Because this substituent, if you look at the all different substituents attached to this guy, they are all different. This is different from this, this is different from this, this is different from this. So this is actually a chiral carbon. Okay? Now, since we established that guy, please go down. Compounds that are optically active are called chiral molecules. Compounds or molecules that are optically active are called chiral molecules. Compounds that are optically active are called chiral molecules. Now let's talk about the next guy, enantiomer. Have you heard of enantiomer before? Yeah. Let's talk about enantiomer. Now, what is enantiomer? Please slow down. Let me define the way that you don't understand. A chiral molecule and its mirror image constitutes a pair known as enantiomer. A chiral molecule and its mirror image constitutes a pair known as enantiomer. Hold on. You're going to find this out. Want one person to redefine this for me. The chiral molecule and its mirror image constitutes a pair known as enantiomer. So now I want somebody to redefine this for me. I just gave us this to help us understand it from the basics. Now imagine you are being called upon. They say, "Hey you, what is enantiomer?" You cannot come and say a chiral molecule and its mirror image. No. So what is enantiomer? Very simple. Enantiomer are pairs of chiral molecules that are mirror image of what? Each other. A pair of what? Chiral molecules that are mirror image of what? Each other. Another question I'd like to ask. Is a chiral molecule optically active? Yeah. It's very simple. Because I also knows that optically active compounds are called what? Chiral. So take note of that. Enantiomer is a pair of chiral molecules that are mirror image of each other. That's what it means. Now, let me use this guy as an example. Look at this compound here. If I come here, I put a mirror here. In mirror image, up and down always remain the same. The up and the down is the same. What changes is the side. What was initially at the right becomes the left. So the mirror image of this guy, I put one here. I put this guy here. This becomes CH2, CH3, and this becomes what? CH3. So this is actually both of them, they are chiral because they have chiral cut. And they optically active. Those are this and this are mirror image of each other. Right? So enantiomer is always known as to be a pair. Pair means how many? Wait, hold on. Let me tell you. This one now you're going to write it by yourself. Remember we say chiral molecules are optically active, right? Yeah. Optically active compounds rotate plane polarized light. Is it not so? Yeah. Now, listen and listen very carefully. Enantiomer contains two chiral molecules that are mirror image of each other. Is it not so? Yeah. Meaning that one out of those two will rotate light to the right, and the other guy will do what? Rotate light to the what? Left. By equal what? Amount. If this one rotates light to the right by 50%, the other guy will rotate to the left by how many? That is it. So, please go down. Let me know before I'm almost on time. Note, a enantiomer that rotates plane polarized light to the right. A enantiomer that rotates plane polarized light to the right is known as dextro rotation. That is symbol of B. of dots. An elastomer that rotates plane polarized light to the right is known as vertical rotation, which has a symbol of D or a symbol of plus. So most of the times, if you open the textbook, you can see something like they can just say butanol. You can see two butanol, and then you see, have you seen long time before? You will see it actually, especially those of us who now because they're going to town. Those of us who use it. Those of us who something concerned now. But it's so boring. Imagine you being extreme that you get it. All right. Similarly, similarly, an instrument that rotates plane polarized light to the left. Similarly, an instrument that rotates plane polarized light to the left is called level rotation. It's called level rotation. Please, if you have your past question, don't start reading abstracted conclusions on that itinerary. Let's break it down. I'm giving you things for that. I cannot be the one taking questions for this thing. If you have past questions, just start reading. Start reading. All right. The last part under this guy, before I move on to the next problem, please pay attention. An instrument comprises of two molecules that are opposite of each other, meaning if one is going to the right, one is going to the left. Now, please write down this last part. A mixture, pardon, a mixture of equal amounts of enantiomer. What's the answer? Resonate mixture. A mixture of equal amounts of enantiomer is called resonate mixture, which is symbolized by plus minus. This is plus minus, so I can say note resonate mixture is optically inactive. I say a mixture of equal amounts or equal quantity of enantiomer is called resonate mixture. And they are optically inactive. I will explain. If you don't have equal amounts, it's not a resonate mixture. Have they made mention of R and X in class for you guys? So now look up. A resonate mixture can only be resonate mixture if the two mixture are equal amount. 50% of this and 50% of this. If I have 60-40 mixture, can this guy be considered a resonate mixture? No.